All right, so now let's see how you can use this idea of projections to construct a numerical method, which again preserves first integrals. Okay. So numerical methods with projection. Okay, so let's say you're given an initial point. Y0, right, and we take a step using a p-order method. Numerical method. Okay, so y1 hat is equal to psi h y0. Okay, so this is the p-order numerical method, right? So what we're basically asking is the following. So if you take one step of this p-order numerical method to give me this candidate solution y1 hat, but this y1 hat is not on the constraint manifold, and then we project it onto the constraint manifold, right? How much, what is the error of decomposition, it's like of the p-order numerical method with the projection step? Okay, so that's more or less the question. So how much of an error, right, do we introduce to the first integral by this step? So first we want to see what the error is, and then the next thing we want to see is what the error of the method is. Okay. All right. Okay. So since the one-step method psi of h is of order p, right? What that means is that y1 hat minus the phi of h, which is the numerical, which is actually exact flow map, y0, right? So I'm comparing the numerical method with the exact solution for the initial condition y0. This is big O of h to the p plus 1. Okay, and then we're going to assume further that I, which is our first integral, is a smooth function. So assume that I is smooth, right? And you also know that if you pull back, it's like the first integral by the exact flow map. It's like you get the first integral, itself, right? That's really the definition of the first integral, right? So if I composed with the exact flow map is equal to I itself, right? Then we have the following. That you can take I applied to y1 hat. Okay, so this is equal to I of y1 hat minus I composed with the exact flow map composed with y0. Okay. And then this thing is equal to 0, at least if we're looking at the 0 level set of the first integral. So this is big O of h to the p plus 1, which, okay. Okay. I guess I should say that you probably have to have one other step. It's like where you use the fact that because I is smooth, it's like it satisfies some sort of Lipschitz condition. And so the difference of I evaluated at y1 hat and I evaluated at this point is some multiple Lipschitz constant times, or it's bounded from above by Lipschitz constant times the distance between these two things, right? So, so going from here to here, right, you want to use that I is Lipschitz continuous. And plus the fact that, again, y1 hat minus the exact flow applied to y0 is big O of h to the p plus 1. Okay. All right. Okay. Yeah, and just so I see it more precisely, right? So since I is smooth, and in particular Lipschitz continuous. Okay. All right. So so that tells you that if you were to just accept it as it is, you just take this one step of the p-order accurate method, then you would drift off. In general, you would drift off this zero level set of the first integral by something which scales like h to the p plus 1. Okay, where h is a time step and p is the order of the numerical method. So let's see now what happens if you then do the next thing, which is that you take this y1 hat as a candidate solution, but then you project back onto the level set of this, the zero level set of the first integral. Okay, so let's see what happens. So in an orthogonal projection method, we solve for y1 such that the following is true. Y1 is equal to y1 hat, which was the candidate solution you've gotten just by directly applying this p-order one-step method, plus lambda times the gradient of the first integral function evaluated at y1. Okay, so this is a sort of implicit type equation, and then 0 is equal to I of y1. Okay, so the problem, of course, as I said, is that this is an implicit system of equations. Right, which in general requires some sort of nonlinear solver to solve for. So we instead consider an oblique projection method. And of course, it's like one of the big problems, right, is that, you know, it's like y1 shows up on both the left and right-hand side. So one very, very natural thing to do is to replace the gradient of I if being evaluated at y1 with the gradient of I being evaluated at something you already know. Okay, so that makes your life easier, because then, again, y1, which is the unknown, doesn't show up on both the left and the right. Okay. So let's see what happens. So given some suitable vector valued function b, of y, right, we have the following oblique projection method. Okay, So again, what you have is that y1 is equal to y1 hat, which was your initial candidate, plus lambda, and instead of the gradient of I, you replace it with b, and instead of evaluating at y1, you evaluate it at y1 hat, which you already know, right? And then again, you write down the condition that y1 is on the level set of the zero level set of the first integral, which is what you want. Okay. And of course, it's like b could be just a gradient. It's like of I, for example, right? So b could be just a gradient of I, for example, right? Okay, so the advantage, if you will, of doing this then is that now you get you still a nonlinear equation, but it's now a scalar nonlinear equation for just lambda. Okay, so this reduces to a scalar nonlinear equation for lambda, right? As opposed to the orthogonal projection case, which which is a vector nonlinear equation. For y1 and lambda. Okay, so and then of course you can solve. It's like this lambda using some sort of Newton type iteration, right? Can solve. Okay. All right, so let's see where we go with this. So we can define a map, say omega h, right, from yn to yn plus 1 by the following, right? So you have sort of what is sometimes called a predictor step, yn plus 1 hat, which is just the one-step method, the underlying one-step method of order p applied to the initial condition, which is yn. And then you have yn plus 1 is equal to yn plus 1 hat, right, plus lambda b y hat n plus 1. And then you have the condition that yn plus 1 is on the 0 level set of the first integral, which is what you want. Okay. So, so it's a bit involved. It's like to analyze the conditions under which this map is well defined, right? So it's involved to analyze the conditions under which this is a well-defined map. Right, and to analyze, it's like the convergence and order of the resulting scheme. Okay, let's erase this first. All right, but under basically mild assumptions on the level set function or the first integral function I and this sort of oblique direction B, right? Under mild assumptions on I and B, right? Can be shown that the resulting function map, it's like omega h, right, generally retains the order of accuracy of the original one-step method, okay, psi of h. Okay, so more or less it's like what we're saying is that, more or less it's like if B is, doesn't become too degenerate, if you will, to the level set itself of I, all right? And then, at least when h is sufficiently small, this method which you have here, it's like which starts off with an underlying p-4 order accurate method, is still going to give you a p-4 order accurate method. It's like when you compose it with projection, okay? And so that's, of course, it's like what you would like to have. Yeah. So that's one possibility. One of the problems, of course, with projection methods is that for many interesting problems, you have multiple, it's like first integrals you like to preserve simultaneously, so it's much more difficult. It's to develop projection methods which allow you to simultaneously project onto the intersection of the level sets, it's like of these first integrals. Okay, so let me just stop here for now.